Good afternoon, sir. My name is Kazilian Rana. My roll number is MEB19011, and this is the presentation for our sessional test 2. Here, coming to the first question. For a flow in the xy plane, the x component of velocity is given by u is equal to this much, where a and b are given, and x and y are measured in feet. Find the possible y component for steady incompressible flow. Is it also valid for unsteady incompressible flow? Why? How many y components are possible? So we are given the x component and we need to find the y component. Okay, so and it is given that it is incompressible flow, because you have to find the y component for incompressible flow. So this entire flow is incompressible. So if the flow is incompressible, it will follow this particular equation, del u by del x plus del v by del y equal to 0. Since it is in two dimensional, we are omitting the del w by del z part, and we are given u is equal to this much, a and b are this much, and we have to find v. So let us say v is equal to v. Let us assume that. So after we put the value of u and v in this particular equation, we will get del v by del y is equal to this much, and which can be further integrated to get the value of v, as you can see here. This is the value of v. Here f of xt is an arbitrary function. However, since we are dealing with a steady flow, there cannot be any function dependent on time. Therefore, in this case, f of xt is equal to fx. As you can see, this we got is f of xt, which will be f of x. That is, the function is purely x dependent. The function fx is, however, completely arbitrary. There are therefore infinitely many possibilities of y component of the velocity. For the ease, let us take the function fx is equal to 0 in this case. This let us take as 0, and this fx is already fx, and this fx is equal to 0. So v will be finally just this. As you can see here, this is v, and after we put the value of a and b as given, we will get v as this. Now this particular solution is not valid for the case of unsteady incompressible flow, because here u is equal to this and v is equal to this, and none of them are, as you can see, none of them are dependent of time, hence making them steady. So let us see, have we answered everything. First we are told to find a y component. So this is the y component, as you can see, this is the y component. Secondly, they have asked, is it also valid for unsteady incompressible flow, and why? And we have answered that here it is not valid, and this is the reason we have given here already. And lastly, how many y components are possible? As you can see, there are infinitely many possibilities of y component of the velocity. Now moving to the second question. Consider the velocity field. We are given a velocity field, as you can see, in the xy plane, where a is equal to this much and the coordinates are measured in meters. Is this a possible incompressible flow field? Calculate the acceleration of a fluid particle at point this. So we are given this field and we need to check if it is an incompressible flow field. So since we are given this, we can obviously break it into u and v, that is the x and y component. And now since we have to check if this one is an incompressible flow field, it has to satisfy this particular equation, del u by del x plus del v by del y is equal to 0. So after we find out del u by del x is equal to this much, del v by del y is equal to this much, and if we add them, we can see they become 0. That is, del u by del x plus del v by del y is equal to 0, hence satisfying this particular equation. And since this equation is satisfied, therefore the given flow field is incompressible. As you can see, it's written here. Then now we have to find the acceleration. So first let us find the x component of the acceleration. The x component of the acceleration is given by ax is equal to u del u by del x plus v del u by del y plus del u by del t. As we can find out, this is the u, this is del u by del x, this is plus v, this is del u by del y, and by del u by del t will be 0. After we put x equal to 2 and y equal to 1 in this previous equation as we got here, and we can get, and also put in the value of a, we have the value of a, we will get ax is equal to this much, this, as you can see here. Then we can find the y component in the similar way. The y component, the formula will be this, and after that this is the u and this is the del v by del x and following, and this del v by del t will be 0. After again put x equal to 2 and y equal to 1, we will get ay is equal to 31.25. So we have got ax and ay. So we can find the net acceleration at 2, 1. This will be the net acceleration, that is under root ax square plus ay square, which will finally give us 69.88. Now moving to the third question. An incompressible liquid with negligible viscosity flows steadily through a horizontal pipe the pipe diameter linearly varies from 4 inch to 1 inch over a length of 6 feet. Develop an expression for the acceleration of a fluid particle along the pipe center line. Plot the center line velocity and acceleration versus position along the pipe if the inlet center line velocity is 3 feet per second. As you can see in the diagram, this is some 4 inch, this is 1 inch, the entire length is 6 feet, and we have to find an expression for acceleration through this is center line. Okay, so we are given the length of the pipe is this much 6 feet, which is 72 inch. The inlet velocity is this much 36 inch per second, and according to a question, the diameter of the pipe changes from 4 inch to 1 inch over a length of 6 feet, and the change in diameter is d minus d, which is 4 minus 1, which is 3 inch. Now let the diameter of the pipe over the length x be dx. See, since you have to find an expression, we will take another cross section at a length x of diameter del x, of diameter dx. This is dx. Okay, so this is dx, and we can see the expression for dx in this way. This is dx. Since as it is given that it is an incompressible fluid flow, so we can say that it satisfies the equation of continuity of one-dimensional flow, that is AV is equal to constant, where A and V are the area of cross section and velocity respectively. So since it satisfies AV equal to constants, we can write A1 V1 is equal to A2 V2. We will write A1 V1 is equal to A2 V2 for this two cross section, this particular cross section and this one. So for this, what will be the A1 V1? The area will be, what will be the area? Let us see. The area is pi by 4 into d square. Okay, pi by 4 into d square. What is d? D is 4. So pi by 4 into d square. This is the A1. And what is V1? V1 is as you can see 36 inch per second square. That is the V1. That is the V1. Then the A2 V2. A2 V2 is for this particular thing. Here what will be the A2? This is pi by 4 into dx square. So pi by 4 into dx square. And what is dx? This is dx. So after we put it over here, and this is the Vx, so we can finally get Vx, and after we put the value of capital D and small d, which we know, this is the capital D and this is the small d, we can finally get an equation of Vx in this way. But now we have to find the acceleration. Now we know that the acceleration of the particle moving only in the x direction with no component dependent on time is this. Okay, see, here we can see that the flow is only in one direction, that is the x direction. So let us just omit the other things and directly write the acceleration this way, as Vx del Vx by del x. Therefore this is Vx, as you can see this is Vx, so we have wrote it here, and multiplied by del V by del x. After we'll partially differentiate this with del x, we'll get this. So the final equation comes up in this way. This is the acceleration equation. Now the first part is solved. Coming to the second part, we have to plot the graph. The first graph is of velocity versus position of particle, where vertical line represents velocity of particle and horizontal line represents position of particle. So this is the position of particle, this is the velocity of particle. When you plot it, we'll get a graph like this, or basically just plotting this thing will give you this kind of graph. And the second graph is of acceleration versus position of particle, where vertical line represents acceleration of particle and the horizontal line represents the position of the particle. So this is the position of the particle, this is the acceleration. We'll get a graph in this way. That is just plotting this particular equation will give us this graph. Thank you.